Maybe you started paying attention to him because of this movie. Or maybe it was this photo that allowed you to see its real existence directly, sparking your interest. Or perhaps, like me, you became deeply curious about it when you accidentally flipped through a science magazine in your elementary school reading corner. In this video, let's learn about it together. Black holes. Let's start with the most basic understanding of black holes and gradually approach the reality of what they are. Newton discovered the law of universal gravitation, which explained why everyone on Earth feels like their head is up and their feet are down, and also why the moon doesn't fall to the ground. Each of us is subject to Earth's gravitational pull, but in fact, this force isn't all that strong. As long as we push off with our feet, we can jump up. For a brief moment, we resist gravity. The greater our initial jumping speed, the higher we can leap, and the longer we can stay in the air. Back in Newton's time, he calculated that if our takeoff speed reached 7.9 kilometers per second, we would never fall back to Earth. We would become a satellite orbiting the Earth just like the moon. This speed of 7.9 kilometers per second is called the first cosmic velocity, also known as orbital velocity. It is the minimum speed required to launch from the Earth's surface and become a satellite orbiting the Earth. In theory, every celestial body has its own orbital velocity, which depends on only two things. Those two things are the mass and volume of the celestial body. It has nothing to do with our own weight. The Sun's mass and volume are much greater than Earth's, and the Sun's orbital velocity is 220 kilometers per second. All this knowledge was already thoroughly understood by humanity back in Newton's era. About 200 years ago, an astrophysicist named Laplace had a sudden thought. What if, one day, the orbital velocity of a celestial body exceeded the speed of light? Wouldn't that mean that even light wouldn't be able to escape from this celestial body? Wouldn't that make the celestial body completely black? He calculated that if the radius of the Sun were reduced to just 3 kilometers, which means its volume would shrink by 1 trillion times, it would become a star that emits no light. Understanding black holes using Laplace's way of thinking is the most straightforward and intuitive method. This is also the level that most people can understand. However, this is not actually the correct understanding of black holes. After listening to me for so long, you must be disappointed to hear that it's not correct, right? But don't go just yet. Next, I'm going to tell you something more advanced. What happened after Laplace? Time flies, and in the blink of an eye, more than 100 years have passed. In 1915, Einstein advanced humanity's understanding of the universe to a realm far beyond Newton. He told us that gravity is merely a manifestation of the curvature of space-time. Newton's law of universal gravitation is just an approximate formula for the true nature of space-time curvature. If the radius of the Sun were really reduced to just 3 kilometers, then the law of universal gravitation would no longer apply. To truly understand the interrelationship between time, space, motion, and gravity, we must use an incredibly complex and mind-bending equation. This is Einstein's field equation. Albert Einstein's theory is the renowned theory of relativity. In 1915, during the height of the First World War, on the front lines where Germany and Russia were fighting, there was a young and brilliant German artillery captain named Schwarzschild. When he saw Einstein's extraordinarily complex and profound equation, he instinctively fell in love with it. While other physicists were still questioning this equation, Schwarzschild had already begun quietly working on the intricate calculations. He spent a long time and finally found a special solution to Einstein's field equation. He discovered something astonishing, a situation that, interestingly, was quite similar to what Laplace had discovered years before. According to his calculations based on relativity, Schwarzschild found that if the Sun were compressed to a radius of 3 kilometers, or if the Earth were compressed to the size of a single chocolate bean, then the space-time at the center of the Earth or the Sun would be curved to infinity. It's as if time and space have tied a knot at this point. Nothing can escape from their surface, not even light. This isn't because the speed of light is less than the escape velocity. In fact, under these circumstances, the very concept of escape velocity no longer exists. Rather, it's because space-time at this point is curved into a deep well. Once light falls in, it can never find a way out. In fact, there simply is no exit. Later on, scientists gave this kind of strange celestial object a name: a black hole. So in fact, a black hole is not actually a hole. In astronomy, it is a celestial body with mass. Black holes are the strangest type of celestial object known in our universe, and we can never see what the inside of a black hole looks like. because inside it, time and space have already become entangled into a knot. You could also say that time and space no longer exist there. A black hole is like a vacuum cleaner in the universe, constantly devouring any matter that comes near it. And once something is swallowed, there's no hope of escaping. In fact, black holes are even more mysterious and bizarre than you might imagine. The so-called size of a black hole refers to the distance from its center to its boundary. Within that pitch-black region, there is actually absolutely nothing at all. That might make you feel quite puzzled. So, where exactly did all of that matter go? Actually, when I said earlier that the Earth could be compressed to the size of a chocolate bean, the truth is that once the Earth is compressed to that tiny size, there is no force at all that can possibly stop it from continuing to collapse. All that's left is a hollow black shell. At this point, someone might ask, so where exactly did all the matter from the Earth go? All I know is that they will keep collapsing endlessly, never stopping. If you ask me what exactly will happen in the end, well, I don't know either. So, let's not ask about it anymore. If you were to ask a professional scientist today, they might answer you in a way like this. Oh, all of this physical matter will eventually collapse into a very, very strange and mysterious point which we call a singularity. Young man, you will surely understand everything when you grow up. Well, honestly, I have grown up now, and yet I still do not quite understand it at all. Precisely because of this, when black holes were first proposed, almost no one believed that such strange celestial objects could really exist in the universe. Later, the famous physicist Stephen Hawking and others discovered that the appearance of such bizarre objects in the universe seemed to be inevitable. As relativity was confirmed by one experiment after another, it further strengthened scientists' conviction. However, there is a very important principle in the scientific spirit. Extraordinary claims require extraordinary evidence. A black hole is clearly an extraordinary claim, so there must be extraordinary evidence to ultimately prove the existence of black holes. So astronomers began a long and arduous effort. For decades, the reality of black holes remained the greatest unsolved mystery in astronomy. It wasn't until the 1970s that astronomers generally speculated that a strange celestial object which had long been puzzling was very likely a black hole. This celestial object, about 6,000 light-years from Earth, emits extremely strong X-rays. At this point, some people might wonder again, isn't it commonly said that black holes don't emit any light? So how can they possibly emit such incredibly intense X-rays? Well, that's because as matter falls toward a black hole, it forms a huge, swirling vortex around it. This is called an accretion disk. So the X-rays are not emitted by the black hole itself, but are produced by the high-speed friction of gases in the accretion disk. These X-rays can be considered indirect evidence of the existence of a black hole, not direct evidence. The first ever photograph of a black hole, taken in April 2017 and released in 2019, revealed the veil of this celestial object to humanity. This photo was the result of joint efforts by over 200 scientists from 20 countries and regions. In order to obtain this photograph, more than $60 million were spent to connect 8 radio telescopes located around the world, forming a virtual telescope with a diameter equivalent to that of the Earth. The shooting lasted 5 days and the collected data reached 7 petabytes. That's like the total photos taken by 40,000 people in a lifetime. Scientists spent 2 years processing data to produce the image. This supermassive black hole in the M87 galaxy weighs about 6.5 billion times the Sun's mass. 55 million light-years away. Note Ultraman is from M78, not M87. Zophy's M87 beam is named for its 870,000 degree heat, unlike Ultraman and Jack's 475 beam at 210,000 degrees. There were even some people, and a very small number of scholars, who still believed that black holes did not exist, but this photograph has silenced them. The existence of black holes has now become an irrefutable and well-established fact. At the same time, it further confirms the precise predictions of Einstein's general theory of relativity, highlighting the greatness of scientists like Einstein and Schwarzschild. Let's give them a triple salute together. In any case, now that humanity has captured the first photograph of a black hole, can the spring of our deeper understanding of black holes still be far away? You still haven't said what a black hole actually is. That's right. After watching this, I still don't really understand what you're talking about. We'll talk about it in the next episode.